Hi everyone, myself Dr. E. Devi, Professor, Department of Electronics and Communication Engineering. In this video, we will learn about the behavior of conductors in electric field. On completion of this video, the learners can understand the basis of behaviors of conductors in an electric field. Before starting this, some introduction part, that is electric field exists in both space and free space and materials. Materials are classified as conductors and dielectrics depending upon their conductivity. So first of all, what is a conductor? A conductor consists of large number of free electrons. When an external electric field is applied, these electrons move until they cancel the internal electric field inside the conductor. So, the conductors have some basic properties. So, let us list one by one. First property is electric field inside the conductor. So, electric field inside the conductor is always equal to 0. The reason behind this is free electrons rearrange themselves to oppose the electric field, creating an induced field that cancels it. The second point is the charge resides on the surface. In electrostatic equilibrium, all excess charge on the conductor resides on the surface. Inside the conductor, the electric field is 0, so no charge can stay inside. So the third property of this is surface of the conductor is an equipotential, that is V equal to constant on the conductor surface, and hence V equal to minus del into V, so that is equal to 0 inside the conductor as per the first property we said. So all points on the conductor have some potential, and inside the conductor this value V is equal to 0. The electric field just outside the conductor. The electric field just outside the conductor is given as sigma divided by epsilon naught into n cap. The electric field is perpendicular to the surface, where sigma is the surface charge density and n is the outward unit normal vector. The next point is Gauss law explanation. Consider an Gaussian surface inside the conductor. So closed integral E dot dA equal to 0, that is equal to E equal to 0. There is no enclosed charges inside is equal number of enclosed charges inside is that field is equal to 0, that is conductivity cavity. Inside the hollow conductor, E equal to 0 even if the cavity has no charges. If the charge is placed inside the cavity, induced charges appear on the inner surface. So electric flux from the conductor, only surface charge contributes to the electric flux, that is phi is equal to Q divided by epsilon naught. So this is a diagram for conductors in an electric field. This is the external electric field E. Inside the conductor, this E value is equal to 0. So induced charges, negative charges and positive charges. So induced charges and internal induced field. So this is the overall diagram of conductors in an electric field. So we have one problem based upon this. The surface given that surface charge density sigma is given as 5.0 into 10 power minus 6 coulomb per meter square. And here you are asked to calculate the electric field outside the conductor. As per the formula we learned just before, E outside is equal to sigma divided by epsilon naught, that is normal to the surface. So calculation of E, step by step procedure. E is equal to substituting the value of sigma, it is given as 5.0 into 10 power minus 6 coulomb per meter square, and also epsilon naught, we know that the constant value permittivity of free space, that is equal to 8.854 into 10 power minus 12. So substituting these two values, our E value is obtained as E is equal to 5.0 into 10 power minus 6, and which is divided by epsilon naught value 8.854 into 10 power minus 12. So the final answer is equal to 5.64 into 10 power 5 volt per meter. This is the value of electric field intensity. So classification of materials. Materials are classified into three categories: conductors, insulators and semiconductors. For example, conductors are copper, aluminium. Insulators are rubber, glass. Semiconductors are silicon and germanium. Conductivity is sigma, determines the behavior. So conductivity and temperature. Conductivity of the material increases, the temperature decreases, and at 0 K some become superconductors. Lead, aluminum will be like that. Superconductor means superconductors exhibit zero resistance and infinite conductivity. Applications are MRI and maglev trains, quantum computers, etc. Non-isolated conductors are connected to voltage source. Charges move continuously. Electric field drives current. Resistance opposes motion. So J is equal to sigma E. For uniform section, E equal to V by I. Therefore, I equal to, substituting this values, J A divided by I into V. So resistance of the conductor R equal to rho into I by A. For non-uniform section, R equal to integral rho by A into dl, that is rho is equal to resistivity in ohm meter. Power calculation, P equal to VI, that is I square R, that is equal to V square by R, defines energy conservation to heat. This is called as Joule's law. Power density is equal to J into E, sigma E square watt per meter cube. Links microscopic field to heat dissipation. According to Joule's law, W equal to I square RT. Heat energy J is proportional to current square of current, resistance and time. So applications of this is electrical wiring, power transmission, shielding and grounding systems. So finally, conductors are playing a vital role for electric circuits and field control. The key principles are Ohm's law, equipotential property, Joule's heating. Hope you all understand this session. Thank you for listening.